Welcome student. PCH 4802 Unit 2 Disconnection Approach. I am Dr. Devanga Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Today we are going to discuss regarding the basic information of disconnection approach, its guideline, functional group interconversion, synthons and synthetic equivalents, etc. Let's begin with the introduction. Disconnection approach, as you know, is a reverse synthesis, and in this reverse synthesis the organic synthesis lies at the heart of science, and compounds synthesized by chemists have played main in the most of the improvements in the quality of life for over last 100 years. Chemist synthesize role is as a chemist, as a researcher, the role is in almost all organic chemistry laboratories in the world. Industrial chemists synthesize compounds, pharmaceuticals, polymers, pesticides, detergents, and disinfectants, cosmetics, and many more. A research chemist synthesize natural products whose structure is uncertain, compounds for mechanistic investigations, possible intermediates in chemical and biochemical processes, thousands of potential drugs for every drug which is in clinical use, and even compounds which might themselves be useful for organic synthesis. For synthesizing a target molecule, that is the end product, the molecule to be synthesized, a synthetic route must be designed to give a pure sample of target molecule using a convenient and efficient procedure which is even cost effective. A given synthetic route is a sequence of reactions designed to convert commercially available starting materials into the desired product. Very importantly said that when we need to decide the synthetic route, initial stages are there where there is no this kind of approach, then people are using trial error method. In this trial error method, they are wasting chemicals, costly chemicals, they are polluting earth, they are wasting their time, and at the end they are not getting anything. While here a given synthetic route is a sequence of reaction designed to convert commercially available starting materials. So from target molecule you need to reach to the starting material into desired product, then we will going to keep it forward reaction and get the desired product. So less chemical has been used, cost effective procedures would be there, starting materials are commercially available, so easily you can start the reaction and get your end product, and even the product percentage would be high as well. Usually the best practice is to devise a number of different routes for a given target molecule and compare them to select the best one, because the time spent is designing a synthesis is far less than that spent in actual laboratory. In general, the best synthesis involves conversion of most available and cheapest starting material into the desired product. Earlier already I have briefed it out by least number of steps. In a very short procedure we will get the product, and in the highest possible overall yield as well. And for that we need to use this a disconnection approach, or we can say a retrosynthetic analysis. We can define as a logical approach for designing organic synthesis which involves breaking down of the target molecule into available starting material by imaginary breaking of bonds, that is called disconnection, and or either by functional group interconversion. When there is no possible disconnection for the starting material, we can use functional group interconversion, and this kind of process is known as disconnection approach or retrosynthetic analysis or retrosynthesis or synthesis backward. This is the process of synthesis design which start with the product and work backward towards the starting material. A double line arrow, this kind double line arrow called a retrosynthetic arrow, this kind of arrow is considered as retrosynthetic arrow, is commonly used to indicate a reaction written backward from target molecule to starting molecule. That is a backward reaction. The actual reaction is in inverse. We can see here a scheme of a retrosynthetic arrow means Z could back be prepared from X plus Y. So here Z is the starting material, and this retrosynthetic arrow will convert them into possible fragments, that is X and Y. So we can use X and Y to prepare Z. We know that the following ester can be prepared from benzyl alcohol and benzyl chloride. Thus we can represent using retrosynthetic arrow the synthesis of this ester on retrosynthesis. This is a retrosynthetic arrow, that is inclined arrow, and it will going to give us benzaldehyde, or we can say benzyl alcohol, sorry, not aldehyde, benzyl alcohol and benzyl chloride. Now the following amide, that is structure 1, can be prepared from para-nitrobenzyl chloride, that is structure 2, and 2,6-dimethyl aniline, that is structure 3. Again, we can represent this using a retrosynthetic arrow. Imaginary breaking of a molecule into its component parts like this is known as disconnection, and it is helpful to indicate disconnection, the site of the with a wiggly line. Usually the reason for making disconnection is shown on retrosynthetic arrow. This indicates the reverse reaction to the disconnection. Here the carbon nitrogen of amide on the retrosynthetic arrow so that carbon nitrogen bond of the amide is disconnected because its formation is feasible. So the feasible site would be disconnected. So here you can see the wiggly line is shown over here for this amide, and that wiggly line shows that the carbon nitrogen bond is to be disconnected from this site, that is known as carbon nitrogen amide disconnection. This is a target molecule, and we are going to get a proposed starting material where this compound is para-nitrobenzyl chloride and this one is 2,6-dimethyl aniline. Now in the case of the above amide, that is structure 1, it was chosen to disconnect from carbon nitrogen bond because this disconnection corresponds to the reverse of a real and workable reaction, formation of amide 1 from amine, that is structure 3, and acyl chloride, that is structure 2. This is the best disconnection of structure 1 because no other possible disconnection of this molecule correspond to the reverse of such a real and workable reaction which yields structure 1. The disconnections are the reverse of a synthetic steps or reactions, and for every disconnection we must have a real and a workable reaction in mind for affecting the corresponding reconnection, that is bond formation, that is forward reaction. Now synthones and synthetic equivalents. Synthones are idealized fragments, we can say reagents, usually cations or anions resulting from a disconnection. Synthones need to be prepared by reagents which is called synthetic equivalents in a suggested synthesis. Let us take the example of paracetamol, which is an amide and can be disconnected either to amide plus acyl chloride or to amine plus anhydride. So here one wiggly line is there breaking this amide bond in the paracetamol. That is CN disconnection put on wiggly line so that it can say that when you need to reconnect this equation, CN bond formation should be taken place. But we get the fragment, that is this two fragment, either this acyl chloride or anhydride we can obtain with this amine. Which reagent is best can only be determined by experimentation, by using it. Commercially, paracetamol is prepared from para-aminophenol and acetic anhydride largely because byproduct acetic acid is easier to handle comparatively with HCl. If we'll take acyl chloride, HCl would be byproduct. If we'll take anhydride, acetic acid would be byproduct. So both the reactions are workable, but we are using acetic anhydride because acetic acid is more easier to handle comparative with HCl. In a retrosynthetic analysis, one should not bother for this sort of decision, which is best made later. Thus, it is useful to have a single way of representing key characteristics of alternate reagents. For example, we can depict both acyl chloride and anhydride in the above scheme as a single idealized reagent of fragments with the cation of electrophilic acyl group, that is CS3 plus C double bond O. Such idealized regions of fragments, usually cations or anions, are known as synthons. Synthon stands for reagents we are going to use in the forward synthesis. They are not themselves reagents because they are charged species. However, they may occasionally be intermediate in the reaction pathway. By disconnecting bonds to synthons rather than to actual reagent, that is synthetic equivalents, we can indicate the polarity of bond forming reaction we are going to use without having to specify details of the reagent. We can apply this idea to the synthesis of the herbicide, that is 2,2-D-2,4-dichlorophenyl oxyacetic acid. The most reasonable disconnection of an ether is carbon to oxygen bond because we know that ethers can be prepared from alkyl halide by substitution with an alkoxide anion. At this stage, we need to decide exactly which alkyl halide or alkoxide to use. So we just write the synthons. Here it is the wiggly line indicating carbon-oxygen bond disconnection. This is our target molecule, the herbicide. So carbon-oxygen, that is ethyl linkage to be disconnected, put on incline arrow, we're going to get our synthon. This one is cation, this one is anion. Once the retrosynthetic analysis is done, we can go back and use our knowledge of chemistry to think of reagents corresponding to these synthons. For example, in the above case, we should certainly choose the anion of phenol and some functionalized acetic acid molecule with a leaving group in alpha position as reagents equivalent to these synthons. Synthetic equivalents are real chemical compounds, that is called reagents, carrying out the function of synthon. Yeah, this is a synthon. This is synthon as well. Now this synthon can be converted to synthetic equivalent by adding the proton over here with base. And here this synthon can be converted into this synthetic equivalent by adding chloride or either bromide. We can get the synthetic equivalent. Sometimes tosyl oxide would be there as well, working as a synthetic equivalent. Then we can write out a suggested, or we can say a design synthesis in full form from the beginning till the end. The suggested synthesis would be like this one. We have taken this proton and treated with a base, followed by this chloride derivative, as it will going to get our ether linkage back, our herbicide target molecule. Now synthon and synthetic equivalents, in which we have this table. These are all synthons and these are synthetic equivalent. So for this positive charge, we can remove the proton and get ketone there. For this kind of, after the carbon of hydroxyl group, if we have positive charge, we can convert it into epoxide. Then if we have this one, we'll convert it to enon. Then if we have nucleophilic carbon, we can convert it into Grignard reagent, alkyl lithium or lithium cuprous alkyd. If we have this kind of anion, we can convert by putting methyl group or this steric group, we can put it and we can get this anhydride. If we have negative charge over here, again the same thing would be there. Some famous definition related to this target molecule we can define as the molecule to be synthesized. Disconnection, that is an imaginary bond breaking corresponding to the reverse of a real reaction. Functional group interconversion can be defined as the process of interconverting one functional group into another during retrosynthetic analysis. Synthetic analysis or retrosynthesis or disconnection approach or synthesis backward. Any term would be asked, you need to define as the process of breaking down a target molecule into available starting material by disconnection and or functional group interconversion using FGIs. Retrosynthetic arrow, that is a double line arrow, that is inclined arrow used to indicate the reverse of a synthetic reaction. Synthon can be defined as an idealized fragments, usually a cation or anion, resulting from a disconnection. Synthetic equivalent, a real chemical compound, or we can say a reagent carrying out the function of a synthon. Now guideline for choosing disconnections. The overall aim of retrosynthetic analysis or disconnection approach is to get back to the starting material that is available from chemical suppliers and to do this as efficiently as possible. The most important task in retrosynthetic analysis is spotting where to make the disconnections. The following guidelines are doing this. Guideline 1. Disconnection must correspond to reverse of real and workable reactions. For that, as we have already mentioned, for every disconnection we must have a real and a workable reaction in mind for effecting the corresponding reconnection, that is bond formation, during the actual forward synthesis of the target molecule. In the case of herbicide 2,4-D discussed above, we chose not to disconnect next to the oxygen atom because we know about the synthesis of ethers. We choose not to disconnect on the aryl side of the oxygen atom as well because we know of no real or workable reaction corresponding to nucleophilic attack of alcohol on an unactivated aromatic ring. Here you can see the disconnection is shown over here, not over here. This is a good choice of disconnection because there is a real workable reaction of this starting material. But if we are going to put wiggly line instead of this, if we are going to put it over here, then it is going to be a bad choice of disconnection because there is not a workable reaction. This synthon will not going to give us a workable reaction. There is no kind of nucleophile can attack to this inactive aromatic ring. Now guideline 2, for compound consisting of two parts joined by a heteroatom, disconnect next to the heteroatom. This guideline works for ethers, amide, ethers, esters, amines, acetals, ketals, sulfides, and so on, because these compounds are often prepared by a substitution reaction. Chlorbenzide is used as a caricide to kill ticks and mites. Using the guideline 2, we can suggest a disconnection next to the sulfur atom, that is heteroatom, and using guideline 1, we know that we must disconnect on the alkyl and not on the aryl side. So here you can see the retrosynthetic analysis. We put the wiggly line over here. We should not put over here according to guideline 1. So we are using both the guideline together over here for chlorbenzide CS disconnection, which is put on this incline arrow, and these are the synthon we can obtain. We now suggest reagent or synthetic coolant corresponding to the synthons and can suggest a synthetic scheme for chlorbenzide. The synthons are like this one, having an ion or negative charge on sulfur, then can be satisfied by putting the proton and base, and this here we can put this chlorine. So this is a dichloro derivative, and this is now this is the suggested, or we can say design synthesis of chlorbenzide. Here our one synthetic coolant, this is dichloro. In presence of base, the linkage would be there and HCl will depart. We're going to get the target molecule back. Retrosynthetic analysis of carbon ethyl ester. We are not expected to predict which base would be used for this reaction. However, sodium ethoxide in ethanol is actually used for carrying out this reaction. This is a mention here just to give an idea of the base strength required to deprotonate ethyl. Let us take another example for illustrating this connection approach for synthesis, or we can say design synthesis. Ketabine ethyl ester is produced to a drug used for lowering the blood lipid level. It is an amine, so we disconnect next to the nitrogen atom. Here you can see next to the nitrogen atom, and using the guideline 1, we cannot disconnect it from aryl side. We have put wiggly line over here. This is our target molecule, and carbon nitrogen disconnection, that is amine disconnection, would be there, and we're going to get this synthon, and this synthon has synthetic equivalent, that is bromo derivative, and this can be converted into this derivative of amine. We do not always need to write the synthon first and then the synthetic equivalents or reagent. If the reagents are simple, we can write them directly as well. For example, the above retrosynthetic analysis can be outlined like this one as well. Here we have put the wiggly line and put a disconnection over here. So instead of putting the cation or anion charges, we can directly put the synthetic equivalent like this. The alkyl bromide is available, but we shall need to make the aromatic monoester, and the best disconnection for ester is carbon-oxygen bond between the carbonyl group and the esterifying group. So here in this ester we put the wiggly line over here, because if we put wiggly line over here, it will overrule the guideline 1. So we haven't put the wiggly line over here, but we have put this CO disconnection, that is amine disconnection, and we're going to get this synthetic equivalent ethanol and this amyl derivative. Now synthesis of ketabane ethyl ester. We can now design the following two-step synthesis for our target molecule, and this is how it was synthesized. You can see the amine treated with ethanol in presence of proton or acid, we're going to get this derivative, and that is treated with bromo derivative in presence of NaOH, we're going to get our target molecule. Now guideline 3, considering alternate disconnections and choose routes that avoid chemoselectivity problems. This can often be done by disconnecting more reactive group first. So here the guideline 3 suggests to disconnect more reactive group first. A reaction in which one functional group within a molecule reacts leaving other potentially reactive functional group unaltered is called a chemoselective reaction. Such a reaction is said to display chemoselectivity. The following compound is an intermediate in the synthesis of potentially anti-obesity drug, that is ICI D7114. With an amine and two ether groups, it requires several disconnections to take it back to the available starting material. Now the question is, which disconnection should do first? So here so many alternatives are there, and we need to choose proper disconnection to get our starting material. One way to solve this problem is to write down all possibilities and see which look the best. In this case, there are 4 reasonable disconnection, one at each of the ether groups, that is suggested route are A and B, and one on each side of the amine, that is suggested route would be C and D. You can see in this target molecule. So here 3 possible disconnection, 4 possible disconnection is there, A, B, C and D. These are the possible disconnection. For route A, these are our synthons. For route B, these 2 would be our synthon. For route C of disconnection, this 2 is going to be our synthon, and for route D, these are 2 going to be our synthon. And we need to decide, after getting these different fragments which are commercially easily available, and after doing reaction, which reaction is going to give us more product, more yield and less byproduct, so that we can get maximum yield out of it. So that is going to be our best path of disconnection out of these 4 possibilities. Now you can see here both A and B disconnection pose problems of chemoselectivity, as it would be hard to alkylate phenol selectively in presence of the basic nitrogen atom. Between C and D, C appears to be the better choice, because the next disconnection after D will have to be an alkylation of oxygen in presence of an amine group. To avoid chemoselectivity problem like this, more reactive group should be introduced late in synthesis. They should be disconnected first. This guideline help us in the next electrosynthetic step of the for the ICD7114 intermediate, that is a drug used for obesity. Disconnection C gave us a compound with 2 ethers that might be disconnected further by disconnection of route E or F. So here you can see that this target molecule would be there. This is going to be E and this is going to be F. Through E route we are doing disconnection of CO ether linkage, and these two synthetic equivalent or synthon we are going to obtain, and by doing disconnection through F we are going to get these two disconnection. Then by doing E again CO disconnection we are going to get these two fragments. Now disconnection E requires alkylation of compound, that is itself alkylating agent. Self-alkylating agent, that means the disconnection F is much more satisfactory and leads to a compound that is easily disconnected to 4-hydroxyphenol, that is phenol, and 1,2-dibromomethane. Using guideline 3, we can say that it is best to disconnect the bromoethyl group, that is route F, before the benzyl group, because the bromoethyl group is more reactive and is more likely to cause problems of chemoselectivity. Now here the guideline design synthesis of ICD 7114 intermediate for used for obesity. This is the hydroxyl group treated with this benzyl chloride. We're going to get this linkage, and treating with dibromo derivative we're going to get this bromo derivative, and treating with the benzyl amine we're going to get the target molecule. Now functional group interconversion, that is FGI. Functional group interconversion is the process of converting one functional group into another during retrosynthetic analysis. FGI mostly involves oxidation, reduction, and substitutions. In the case where we do not have a real workable reaction reverse to a disconnection, we must therefore first choose FGI to change a functional group into another suitable group for a good disconnection. For example, in designing a synthesis of a local anesthetic, that is benzocaine, we know that ester are made from alcohol and acids, so we can write a CO disconnection there. This is our analysis 1, where CO disconnection of this target molecule, estery linkage is disconnected. You need to put big incline arrow. This is by mistake shown the simple arrow. It should be incline arrow, and we're going to get this synthetic equivalent. Second possible route, we should now like to disconnect carboxylic or amine from aromatic ring, but we do not know of any good reverse reaction corresponding to these disconnections. We must therefore first do FGI to change this functional group into others which can be disconnected satisfactorily. Aromatic acids can be made by oxidation of methyl groups and amino groups by reduction of nitro groups. We can write this reaction like using these two. So here carboxylic group and amine is there. Using functional group interconversion we can convert it into nitro group, and on FGI instead of carboxylic group we can get here methyl group. This can be after the oxidation we can get this one, and after the reduction nitro group can be converted into amine. So these two information, that oxidation and reduction, can help us to get our this target molecule. So we are telling about the forward reaction on the incline arrow step. Now disconnection of nitro group is rational because we know that nitration of toluene occurs easily and toluene is available commercially. So we can use this after the functional group interconversion. We can use this disconnection and we can get toluene as our starting material. This complete the retrosynthetic analysis, and we should now write the design synthesis. We should not expect to predict the reagents and conditions. It is sufficient to be aware of type of reagent needed. Here actual reagents and conditions are given just to help broaden that awareness. This is the design synthesis. We have toluene on nitration. We can get the nitro derivative of this toluene. Now on oxidation, we're going to get this carboxylic group, and then doing the reduction, we're going to get the amine group over here, and treating with ethanol and in presence of acid, we're going to get our ester. Functional group interconversion, another example. FGI also often aid disconnections where correspond to be disconnected are more reactive than reactants, because in such cases there are chemoselectivity problems. In these cases, the compound to be disconnected is converted into a less reactive one by FGI before the disconnection. Let us illustrate this by taking an example of following amine synthesis using FGI. This is the target molecule CN, that is amine. On disconnecting from this side, we're going to get this amine and this halide group over here. Now here the problem is that the product, or we can say the target molecule, is usually more reactive than the starting material itself, and there is danger of multiple alkylation, and we're going to get bigger chain of the molecule. So FGI is used to overcome this problem, and the reactive amine is converted into a reactive amide before disconnection, and the reduction of amide to amine is quite reliable, and so FGI is a reasonable option over here. So here you can see that we have done the FGI, functional group interconversion, and this carbon nitrogen is converted into amide linkage, and then the disconnection is taken over here. We have put the wiggly line, and on incline arrow we have written CN, that is amide, disconnection, and we're going to get our starting material. Now design synthesis of amine, that is amine group treated with acid chloride. We're going to get this amide, and on reduction with lithium aluminum hydride, we're going to get our target molecule, and we avoid that problem of more alkylation with the target molecule. Now alternate route is to convert the amine to an imine, which can be disconnected to amine plus carbonyl compound. This approach is known as a reductive amination. So here retrosynthetic analysis, functional group interconversion, we put here double line, unsaturation would be there, so it is converted into amine nitrogen. Now we will going to put wiggly line over here to disconnect this amine nitrogen. We're going to get this amine and this group alcohol as well, aldehyde as well, sorry. Now this is a design synthesis, aldehyde treated with amine in presence of acid catalyst. We're going to get this imine linkage, and then treating with sodium boron hydride, reduction would be there, and we're going to get the target molecule. So these are the two workable options using FGI. Well, this is enough from my end. Thank you very much for paying attention to this video lecture. Keep asking questions. As you know, asking question is a beautiful way to gain knowledge. Thank you.